All right, class. This is, I believe, where we left off last class or last lecture. So we really finished off looking at some of the properties of water. And so as we continue with that, I kind of left us with this particular slide, even though it's still discussing water. Now, the reason I left it here is because at this point, we're now starting to talk about what happens with water when it dissociates. And that kind of leads us right into the next section that we're going to talk about regarding acids and bases. And so when we look at water, one of the characteristics of water is that it spontaneously dissociates to form specific ions. One of the things you're going to see down here at the bottom is that you'll see kind of this equation. And we'll touch on that equation here shortly, but you'll notice that when water reacts with water, you're really looking at two individual ions that it produces. So we'll discuss that here in just a second. But when we look at water and how it dissociates, we have to look at the bonds between oxygen and hydrogen. And those bonds will actually break apart spontaneously. And it does this at a rate of about 1 per 10 million ions per liter. And so what then ends up happening is we look at that OH group, and that OH group is called a hydroxyl ion. And then we also look at a hydronium ion, okay? So we have a hydroxyl or a hydroxide ion that's OH negative. The hydrogen ion then is actually transferred to a second water molecule, and that gives us a hydronium ion. Now, hydronium ion is often referred to or is indicated by an H plus, because again, you take H3O, you pull out the water, you're really left with what we would consider a proton. And so if we look at this hydronium ion, again, I said, oftentimes you'll see it indicated as H plus, as I have indicated there. Essentially, if you look at H, which is hydrogen, and it indicates a positive charge, when you see that positive charge, it basically means it's lost an electron. And so at this point, we are looking at, sometimes we'll call this as being just a proton. But again, it's a hydronium ion. It's got an additional hydrogen ion to the water, and that therefore gives it a positive charge. We're typically going to see when water reacts with water, equal numbers of positive hydrogen ions and negative hydroxyl ions are produced. And so what that means is that when water reacts with water and it dissociates down, we're always going to see a situation where it's the H3O plus, one ion of that, and OH minus, one ion of that. But we can simplify that down and essentially pull out kind of one of these water molecules and simplify it to one molecule of H2O or one molecule of water dissociates down into H plus and OH minus. And so that's kind of looking at water as a neutral solvent. And we're going to see the characteristics of why this is important here as we start talking about acids and bases. So as we look at acids and bases then, the first thing we're going to look at is an acid. And acids are typically going to dissociate in water, and they're going to produce an excess amount of hydronium ions and another particular anion. So it's going to have some additional negatively charged product. We typically refer to these as proton donors because, again, as indicated before, we oftentimes call the hydronium ion a proton, and so we consider these proton donors. They are going to increase the concentration of free hydronium ions. And so that's actually going to indicate kind of the strength of an acid. And so as we dissociate more hydronium ions into the solution, we are actually going to see stronger acids. So for example, HCl in the stomach. HCl is a very strong acid, hydrochloric acid. And when you dissociate HCl into water, it actually releases a lot of the hydronium ions into that particular solution. In weaker acids, we're actually going to see less dissociation of the hydronium ion. And again, an example was going to be carbonic acid. Carbonic acid, again, a very weak acid. So when it dissociates, it actually only dissociates a small amount of hydronium ions. So if we look at this equation down here at the bottom, we see substance A, which is going to represent any particular acid in water. It's going to dissociate down into the hydronium ion and some additional anion. We're releasing these protons and some negatively charged ion into solution. Now, if we look at a base then, bases are going to accept the hydronium ions when added to solution. So they are what we consider proton acceptors. They're going to decrease the concentration of free hydronium ions by absorbing it with the utilization of bases, or with the utilization of that hydroxyl ion. So we can also look at it this way. While bases decrease the concentration of free hydronium ions, they also tend to increase the concentration of hydroxyl ions. And that hydroxyl ion, remember, is OH minus. And so when these bases release OH minus into the solution, you'll notice that OH minus is probably going to want to react with the hydronium ion, or H plus. And so what it does is it absorbs the hydronium ion of stronger bases. An example would be ammonia and bleach. Those are going to be very strong bases. But then we also have some less or some weaker bases, and they absorb less hydronium ions. And this is going to be the bicarbonate ion in the blood and in secretions released into the small intestines. And what it does is it kind of acts almost as like a buffer by helping to stabilize or maintain pH within the bloodstream or within the body itself. And so again, when we look at substance B, a base in water, plus the hydronium ion, now we get B, the base, plus the hydronium ion. And so again, we're kind of pulling hydronium ions out of solution. So if we look at what pH then is and how it actually acts, or how these hydronium ions and hydroxyl ions are interacting together, we have to really look at pH and understand what pH actually is. And so pH is really a measure of the hydronium ions in concentration. And so we have a relative amount of hydronium in solution, and that's going to give us a pH that's going to range between 0 and 14. Typically, we look at the pH of plain water, or very equal water, if you will. It's going to be 7. So it's got a very neutral pH. This isn't water that has a lot of other ions and stuff in it. It's simply plain water, all H2O. So water, again, we said dissociates to produce 1 per 10 million ions of hydronium and OH ions per liter. And so that is equal to 1 times 10 to the minus 7th. Or if we put it in decimal points, it's 0.6 zeros and a 1. And so in order to calculate concentration, you're going to use the negative log function on your calculators. And so it becomes the negative log of the hydronium ion concentration. And so if you happen to put the negative log of 0.6 zeros and a 1 into your calculator, that should give you an answer of 7. And so the pH and the hydronium concentration are inversely related then. And so it's inverse of the log for a given hydronium ion concentration. So what we see then, as the hydronium ion concentration increases, the pH then decreases. Okay, so we have kind of that inverse. So as the hydronium ion concentration decreases, the pH then increases. So you are going to see, again, with acids have more hydronium ions in them. So as the hydronium ion concentration increases, let me try to type that in there, you're going to see the pH go down. And so acids have a lower pH. So they're on the 0 to 6.99 scale. When we look at bases, we look at where the hydronium ion concentration decreases because the hydroxyl ion increases. And so because of that, you're going to see the pH increase. And so this is going to take us to a pH of 7.01 up to 14, whereas with acids, we're going to have a pH of 0 to 6.99. So those are kind of the pH ranges that we're going to see with acids and with bases. So if we kind of look at that interpretation of the pH scale, we kind of get a chance to kind of review what we just said. When we look at the pH scale and we look at the neutral pH, this is essentially water. It's where we have a solution with equal concentrations of hydronium ions and OH ions. And so what that does is those two ions basically are able to interact and pull equal numbers of each other out of solution, so it maintains a neutral pH of 7. As we start to add more hydronium ions, we're going to start to see the pH go down. Again, these are acidic solutions or acidic substances. And again, they have the solution with a greater number of hydronium ions than hydroxyl ions. We also then look at the basic component, or what we consider alkaline solutions. These have a greater hydroxyl ion concentration than they do hydronium ion concentrations. So we're pulling more hydronium ions out of solution, and so that's actually going to give us a pH greater than 7. And one of the characteristics of this pH scale is that as we move from one number in the pH scale to the next, it's actually a tenfold change in the number of hydronium ions that we actually have. So, for example, a pH of 6 has 10 times greater concentration of hydronium ions than pure water, which has a pH of 7. So again, each number, each pH whole number has a tenfold change in the number of hydronium ions. So if we take a look at the pH scale, this gives us a chance to kind of look at a few substances that fall within that scale and where they actually fall. You can see a very strong acid is going to be hydrochloric acid, HCl. Lemon juice and stomach acid is about 2 to 3. And so these are going to be very strong acids. They put a lot of hydronium ions into concentration or into solution, and you can see that over here. When we look at the basic component, now we're looking further down the scale, you'll notice that there's fewer hydronium ions in that solution, which means we have a higher pH. So these are more alkaline or basic solutions. So how do we keep everything neutral or return everything back to a neutral pH if we need to? Well, acids are neutralized by adding some sort of base to it. Again, acids put hydronium ions into concentration. Bases put hydroxyl ions into concentration. So if you add a base to an acid, it's going to pull those hydronium ions out, and that therefore is going to increase the pH. And so that's how we tend to neutralize stomach acids with acid reflux. We basically are trying to stimulate an increase in some of the pH, slight increases in the pH within the stomach. Bases, therefore, are then neutralized by adding an acid. So if we have a pH that's too high, we want to add something that brings that pH down, and that's going to be our acids. Now, we also have what we call buffers. And buffers are really there to help pH changes if some sort of excess acid or base either is added or begins to accumulate in an area. They can act to accept hydroniums from excess acids, or they can actually donate hydronium to neutralize a base. So for example, we have carbonic acid and the bicarbonate ion. Carbonic acid is a weak acid, bicarbonate is a weak base, and they help to buffer the blood pH. And both help maintain blood pH in the critical range. And you'll notice the critical range for blood pH is slightly acidic, around 7.35 to 7.45. And so it's really important for our bodies to be able to maintain that pH in order to optimize a lot of function. So now let's look at starting to add things together. And this is where we start looking at mixtures. So mixtures are going to be formed by combining two or more substances. We mix them together. There are a couple defining features on mixtures in particular. We have to look at the substances mixed and note that they are not chemically changed. Understand there's a difference between physical and chemical changes. And the substances, therefore, can also then be separated by some sort of physical means. So we can evaporate it or filter it. Evaporation involves just a slight change in temperature for evaporation or to essentially boil something off. And filtering, we obviously just put a barrier in there. So when we look at the three categories of water mixtures, one of the first ones we look at is a suspension. And a suspension is where the material is larger in size than 1 millimeter is mixed with water. So we look at blood cells that are mixed within plasma, or we can look at sand within water. If we look at these two examples, we'll notice that when we think about how they separate, they really do not remain mixed together unless there's some sort of motion within that particular system. Typically, it's going to appear cloudy or opaque, and this particular type of mixture, this suspension, is actually going to scatter light. And so if we think about sand and water, you spin it around in a bucket, it'll kind of mix together, but as you let that bucket sit there, it's actually going to start to settle out. When we look at a colloid has much smaller particles than what we see with a suspension, but they're larger than those in a solution. And so when we look at an example of a colloid, this is where we have fluid in the cell cytosol and fluid in blood plasma, okay? Again, these substances remain mixed even when they're not in motion. And they also scatter light. And so our last one then is a solution. Now, a solution is a homogeneous mixture, and it has material that's actually smaller than 1 nanometer. It does dissolve in water. It does not scatter light and does not settle out if the solution is not in motion. So, for example, sugar water or salt water or blood plasma. All of these examples are a type of solution. Specifically, think about salt water. You go to the ocean, you pull a bucket of salt water and you let it sit, that water is not going to settle out. The salt's not going to settle out in the water while you wait for it. And so again, we're looking at where these structures are very, very small. And think about salt water. Think about NaCl. And think about when it gets put in water. It's an ionic substance or ionic bonds. And so the water, because of its electronegativity on the oxygen and the electropositivity on the hydrogen, is going to go in and break up that NaCl, those salt crystals. And so now you basically have ions of sodium and chloride that's being pulled apart. And so there's only a couple ways that we separate those. Now, if we kind of look at this special category of a suspension, it's called an emulsion. And this is where water and some sort of nonpolar liquid substance kind of gets mixed together. And so we see oil and vinegar, salad dressing, or breast milk. If you've ever seen breast milk settled out, you'll see the two layers, specifically like in pumping bags where it gets stored. As you start to thaw it out, you'll see the separation of the substances. Same thing with oil and vinegar. Now, if you shake them up, you get a chance to kind of mix them. But once you let them sit, they'll start to separate just a little bit. So if we look at a couple of these examples, I'm not entirely sure how this image shows up on your screen. You should have it in your notes. You also should have it in your book. So you can kind of go back and look at that, and hopefully it's a little clearer if this is not. And so if we look at a couple of these mixtures, particularly we look at a suspension. And if we look at a suspension, you'll notice that it does separate out. Now, typically one of the ways that we let it separate out is oftentimes we spin it. We put it in a centrifuge. We kind of force some of those things to separate out a little bit more. But otherwise, if we just kind of let it sit, you'll notice that they separate anyway. Centrifuge just kind of speeds up that process. If we look at a colloid, this is more of a gelatin. So think of Jello and think of putting different fruits in it. The fruits are within that colloid. They're certainly not the same. They can be separated out, but that fruit or whatever you put within Jello kind of suspended within that colloid. And then we have a solution, which again we kind of touched on. Very small particles. Think about salt water. One of the only ways to separate it is by some sort of physical means. And so we basically increase the temperature of salt water. We boil off the water, and we are then left with the salt crystals. So as we start to look at these solutions, we have to look at the concentration of what's in them. And so the concentration is actually determined by the amount of the solute that is dissolved within the solution. We can express these in a couple different ways. How we express concentration is mass per volume in one way. And this basically is the mass of the solute per volume of solution. So you can see grams per liter or grams per deciliter. We also oftentimes see this particular expression when we look at a blood test. I don't have, if I had one to show you, I'd actually pull one up, but when you look at a blood test and you look at the samples and you look at both the present value and what a normal value is, you'll oftentimes see grams per deciliter or however they're reporting a particular substance within the blood. We can also express concentration by mass per volume percent. And so we'll have grams of solute per 100 milliliters of solution. And so you oftentimes see a 5% solution or a 10% solution. And this is how we oftentimes see IV solutions labeled when they're in the IV bags. We can also report it or display it as molarity. This is somewhat of a common way that we utilize for calculations. And this is where we calculate moles per solute or moles of the solute per liter of solution. And so you'll oftentimes see a half a molar solution, and we represent molarity by a capital M. So a 1 molar or a 2 molar solution means there's 2 moles of solute per liter of solution. Molarity can alter with changes in temperature based on what the structure does and how it breaks down. And molarity is more easily measured in the body than what molality is. Now, molality is the next thing. This is moles of solute per kilogram solvent. And so molality does not alter with changes in temperature, and it's slightly more accurate than molarity. Now, we also start to look at osmoles. And so osmoles is the unit of measurement for the number of particles that we see in a solution. And so what osmoles does is it reflects whether a substance dissolves or dissolves and dissociates within that particular solution. It can be expressed as osmolarity or osmolality. Again, going back to what we just talked about, osmolarity is the number of particles in a 1 liter solution. Again, it's easy to measure. We do this with blood serum. It's expressed as milliosmoles. And then we also have osmolality. And osmolality is the number of particles in 1 kilogram of solution. And it's more accurate, but it is difficult to measure. So going back to osmolarity and molarity, we then have to look at what a mole actually is. Now, when we look at moles, this number here is probably something that you'll end up, if you haven't already from high school chemistry or whatnot, will commit to memory. It is Avogadro's number, and Avogadro's number is 10.022 times 10 to the 23rd. And what that means is that we have that many number of atoms, ions, or molecules, depending on what we're looking at. And so we look at the mass in grams of a particular substance is equal to the atomic mass of an element or the molecular mass of a compound. So if we look at what this means, we know what the atomic mass is. So for a carbon, the atomic mass is going to be 12.01. It's the number in the square, that bottom number of the square of the periodic table. But let's say, for example, we have H2O, and I apologize, I don't have subscripts easily accessible. So we have H2O. So the easy way to do this, and I'm again kind of going off memory here, hydrogen has an atomic number of one, or atomic mass of 1, roughly, and oxygen has an atomic mass roughly of 16. And so in order to get the molecular mass, we add the mass of all of the atoms within that particular chemical formula. So in this case, we have 2 hydrogen atoms. So 1 for hydrogen times 2 atoms gives us 2, plus the 1 atom of oxygen is 16. H2O then has a molecular mass of 18. And so 18 grams, basically, of H2O has 6.022 times 10 to the 23rd molecules of water. And so that's how we kind of calculate this. Now you can do this for basically any molecular component or any molecular compound. You just add those up, and that's how many grams is 1 mole. And then from there you can do your calculations as you need to. So again, to find the molecular mass, you multiply the number of units of each element by the average atomic mass and add those totals. And there may be some variation, again, obviously due to isotopes and things like that, but for the most part, this is the basics. Whoops. This is the basics of what you're looking at when it comes to molecular mass. So the next little section that we get into here then is where we start really looking at the biological macromolecules. And so we start looking at a few characteristics of these things. With biological macromolecules, these are going to be very large organic molecules that are synthesized by the body. Now, one of the things I guess we need to know is, what is an organic molecule? Well, specifically, organic molecules really relate to things that contain carbon. And so we kind of see this down here, where organic molecules always contain carbon, hydrogen, and oxygen. Now, organic chemistry really refers to things that contain carbon. That's really what we call organic molecules, things that contain carbon. But because of the structure of carbon, we oftentimes find hydrogen and oxygen involved. Other things that may be involved or contained within organic molecules are going to be nitrogen, phosphorus, and or sulfur. The carbon skeletons can really take a variety of forms, from ring structures to chain structures to branch structures to acid groups, to all different types of things are involved with organic chemistry and carbon skeletons. Hydrocarbons are going to be organic molecules that only contain carbon and hydrogen atoms, therefore the term hydrocarbons. Other biological macromolecules, however, are going to contain functional groups. And these functional groups are really going to identify what type of molecule it really is. Most of these functional groups are polar and are going to be able to hydrogen bond. They can form these bonds typically with water because, again, of the electronegativity and positivity of the water molecule. Some of these functional groups are going to act like acids. For example, the carboxyl group, which is going to be a COOH group. And what that means is that COOH is going to be a carbon that's double bonded to one oxygen and then single bonded to another hydroxyl group. So that's what we're going to see with the carboxyl group. We also can have an amine group, and the amine group is going to act like a base. And we're going to see that when we talk about amino acids, and we'll talk about that group a little bit more a little bit later. So when we look at some of these other molecules, we also look at what we call polymers. Now, if you remember, or you've had some of this before, you look at your prefixes. Poly is going to mean many, and you'll see down here mono means one. Another term, another prefix we'll see is di. Di is going to indicate two. And so these molecules, polymers, are typically made up of monomers, which are repeating subunits. So we're going to see carbohydrates are going to be polymers, and they're going to contain sugar monomers. Nucleic acids are going to contain nucleotide monomers, and proteins are going to contain amino acid monomers. So as we start to look at all these macromolecules and we look at some of the characteristics, we kind of have to understand how we form them, but also how we break them down. And so that leads us into two of these reactions that we're going to discuss. So the first reaction here is a dehydration synthesis, or what we consider a condensation reaction. A dehydration synthesis occurs during the synthesis of biomolecules. So when we are creating specific molecules, typically what we're going to see is one subunit is going to lose, sorry about the typo there, one subunit loses an H, or a hydrogen ion or hydrogen atom. The other subunit loses an OH molecule. And so basically, as we pull out the OH and we pull out the H, those combine to form a water molecule, and we have a new covalent bond formed, and the water is produced. When we look at hydrolysis, is going to be the opposite. Hydrolysis occurs during the breakdown of biomolecules. In this case, we add water to the equation and to the reaction. And so we add hydrogen is added to one subunit, and the OH, or the hydroxyl group, is added to another subunit. So if we take a look here then, here we have monomer 1, monomer 2 in a dehydration synthesis reaction. We take the hydroxyl group of one monomer, we take the H off of another hydroxyl group. Those are going to form a water molecule, and then we're left with this monomer bound to an oxygen, which gives us a dimer. And so as we start to repeat that here, and then here, and here, and so on and so forth, that's going to give us what we consider the polymer. And so we're creating these elongated structures by continuously pulling out a water and creating new bonds. Now, if we go through the hydrolysis reaction, we're now going in reverse. We're adding water to the system. Again, here comes the water, here comes your dimer. We add water. Here's the OH, or the hydroxyl group, to one monomer. Here is the hydroxyl group, or the hydrogen, that's added to the other hydroxyl group. And now we're back to our original monomer molecules. So one of the things that we're going to look at then, as far as biomolecules, or the larger biomolecules, are going to be lipids. And lipids are a diverse group of fatty, water-insoluble molecules. When we look at lipids and fats, they're going to be used as stored energy. We're going to find them in a lot of our cellular membrane components. And then we also see them function as hormones. And we have four primary classes. We have a triglyceride, a phospholipid, a steroid, and eicosanoid. So if we look at triglycerides first, they're typically used for long-term energy storage. As the name suggests, we're actually going to have three fatty acids. So we got three. And then we have a glycerol backbone. So three fatty acids and a glycerol backbone. So that gives us three, or a triglyceride. When we look at fatty acids, they're going to vary in length as well as the number of their double bonds. If we look at what we call a saturated fatty acid, that's some sort of fatty acid or lipid that does not have any double bonds. Everything is single bonded. So I'm going to try my best to type this out here. If we take a carbon, bond to a carbon, bond to a carbon, bond to a carbon, and we just continuously do this, this is what we consider a saturated fatty acid. Now again, carbon, remember, has 4 pairs of electrons, so in this case, every single carbon is going to max out on the remainder of their bonds with a hydrogen molecule, or in this case, it could be something else, but Every single carbon is going to have 4 individual single bonds. An unsaturated fatty acid is at least going to have 1 double bond. So we'll see a bunch of carbon here. There's a double bond. So in this case, we have at least 1 double bond. Okay, so this is an unsaturated fatty acid. If we have a polyunsaturated fatty acid, now we're looking at a situation where, we have at least 2 double bonds. This is what we consider a polyunsaturated fatty acid, 2 or more double bonds. Now, adipose is one type of fatty acid or one type of tissue, and it stores triglycerides. There are 2 processes that we look at when we look at adipose tissue. We have lipogenesis, and lipogenesis is actually the formation of triglycerides when conditions of excess nutrients exist. So as we have too much of certain substances, we can actually form adipose tissue or form fat tissue. If we need to break it down, then we go through lipolysis. And this is where we break down triglycerides. And we do this when nutrients are needed. So we break down fatty acids, we break down fat tissue. Again, because of fat tissue and what its function is for long-term energy storage, we can break down the fatty acids to gain additional nutrients. So here's a few examples of what here's an example of what a triglyceride looks like. You can see all of these formations, your glycerol backbone, your 3 fatty acid chains, and how they actually bond to the glycerol backbone here. Again, we're pulling water out of each of these equations or each of these bond forming structures to give us this particular triglyceride here. So if we go through lipogenesis, this is where we form a triglyceride. So we're forming it here on this side. Here where we go through lipolysis, and we actually break down that triglyceride and bring it back into its component parts. So if we look at our next one then, the next type of lipid, it's a phospholipid. So phospholipids are amphipathic molecules, which means they have both polar and nonpolar sections, and they form chemical barriers of the cell membranes. Remember, with phospholipids, we have kind of a water-fearing side and a water-loving side. The phospholipid structure is similar to a triglyceride, except that one end of the glycerol has a polar phosphate group. So we have a glycerol, a phosphate, and the organic groups are all polar, and they're going to form what we call the hydrophilic head. We also then have the fatty acid sections. Those are going to form the hydrophobic tails. So we have the polar heads, which are water-loving, and we have the non-polar tails, which are water-fearing. Our next type is a lipid, is a steroid. When we look at steroids, we typically don't talk about these very much, but they're actually composed of hydrocarbons that are arranged in a multi-ring structure. These are 4 carbon rings. They have 6 carbon atoms, and one of them is a 5 carbon atom. And so what they do is they differ in their side chains that extend from their rings. So cholesterol is actually a really good example of a steroid. And it's one of those things that it has, in the history, or in the recent history, kind of has a bad name. Everybody hears cholesterol, they think too high, they think heart disease, vascular disease. But the reality is cholesterol is both a good and a bad thing. Too much cholesterol, can obviously cause a few health problems. But cholesterol itself is a really good thing because, 1, it's a component of our plasma membranes. Number 2, it's a precursor to other steroid it's a precursor to other steroids that we actually need to create. But then number 3, and you'll notice here, it's a precursor to vitamin D. And more research continues to be done on vitamin D and its health benefits. And vitamin D is extremely important in the immune response. It's been shown to be very effective in helping with the flu. It just in general has a lot of good immune response benefits. The interesting thing is your body can create it naturally, and it does it by being out in the sunlight. Your skin will actually help to create vitamin D. And so that's kind of a big part of why a lot of people, one, don't get as sick or get sick in the summer as much. Obviously, the other reason is we're oftentimes outside, and so we don't have that close contact that we do typically through wintertime. But again, the other reason is because our vitamin D levels continue to be high because of the sunlight. We'll also see steroid hormones, testosterone and estrogen are also classified as steroids, as well as bile salts. Now, eicosanoids, we don't really go into too much depth with these. We kind of get through these pretty quick. They're modified 20-carbon fatty acids. They're synthesized from arachidonic acid. They are a membrane component. They're utilized for local signaling molecules. Their primary function is in the inflammatory response, as well as nervous system communications. And you'll see here we have 4 classes: prostaglandins, prostacyclins, thromboxanes, and leukotrienes. Again, immune response, blood clotting, inflammatory response. So again, all things that are important in that function. So now if we look at a little bit of a clinical view for fatty acids, both saturated, unsaturated, and trans fatty acids, most animal fats are saturated, which means they're solid at room temperature, and most of these are going to be single bonded structures, single bonded carbon atoms. Most vegetable fats are unsaturated, which means they have some double bond, or at least one double bond in them. Most of these are going to be liquid at room temperature. They typically are healthier than the saturated fatty acids, and they can be converted to saturated fats through hydrogenation. So it's, again, also kind of one of those things that your body can go through a process where just because you're getting unsaturated fatty acids into your system, at some point there could be some reactions that actually cause them to convert to saturated fatty acids. Partial hydrogenation can actually lead to trans fats. And trans fats are what we typically think of when we think of really bad fats. They increase the risk of heart attack and stroke. So as we start looking at transitioning from fatty acids and lipids, we now start to look at carbohydrates. Now, carbohydrates are typically what we think of when we think of different types of sugars and starches. So what carbohydrates do, they have a hydrogen and a hydroxyl group, and they're usually attached to every carbon. So what we're going to find is that the chemical formula for carbohydrates typically is going to be CH2O to the nth. Now, what that means is you take N and you kind of throw in a number. So if you think about what glucose is, C6H12O6, you throw a 6 in that N spot, you multiply it through, you get C6H12O6. And so that's the typical type of chemical formula for a carbohydrate. We can have what we call monosaccharides. Monosaccharides are simple sugar monomers. We can have disaccharides. Disaccharides are going to be formed from 2 separate individual monosaccharides. And then we have polysaccharides. Again, poly meaning many. So this is going to be formed from many monosaccharides. We also have glucose. Glucose is a specific type of carbohydrate. It's a 6-carbon carbohydrate with a chemical formula of C6H12O6. Again, as before, we said it's the most common carbohydrate, most common monosaccharide that we have in our body. It's the primary nutrient that supplies energy to cells, and the concentration must be carefully maintained. Too low is probably one of the big things. We don't want too little glucose because, in particular, our brains have a very significant need for glucose and for energy. And without it right away, that can cause some damage or some lack of function to those particular areas. Glycogen is a very large carbohydrate. It's essentially a way that we store glucose. It's stored in the liver and skeletal muscle, and it, again, binds glucose monomers together. We do this through a process called glycogenesis. where we take a glucose molecule and bind it to another glucose, to another glucose, to another glucose. And we do this continuously. We also can break down glycogen. Again, glycogen primary function is for storage of glucose. And so as our bodies need more glucose, we can actually pull it from our glycogen stores. We go through glycogenolysis and we actually break it down into our individual glucose molecules. And so here we get a chance to kind of see the two processes. We can go through glycogenesis or glycogenolysis, and we actually look at what happens. So we can see a situation where we are forming, here's an individual glucose, here is a bunch of glucose molecules that have been formed together. And this is what we look at when we look at glycogen, a bunch of glucose molecules put together. If we need to break it down, we go the opposite way. We break individual glucose molecules down into the component parts, individual glucose molecules. We do have some other types of carbohydrates. We can have hexose monosaccharides, which are glucose isomers. This would include galactose and fructose. We can have 5-carbon monosaccharides, which would be considered pentose sugars. This is going to include ribose and deoxyribose that we typically find in RNA and DNA. We can have disaccharides. Disaccharides are 2 simple sugars bonded together. Some of the common ones are sucrose, lactose, and maltose. These are all disaccharides. These are all glucose molecules bonded to some additional second hexose monosaccharide. So all 3 of these have some sort of glucose together. And then we also have polysaccharides. And polysaccharides are going to have 3 or more sugars. Glycogen obviously is the most common in animals. It's the way we store glucose again. And then we also have starch and cellulose, and these typically are found in plants. And so plant starch is a major nutritional source of glucose for humans, whereas cellulose typically is a source of fiber or some sort of non-digestible structure. Here are some of our simple sugars. You can see the monosaccharides. These are 6-carbon sugars. Here's galactose and here's fructose. Here's our 5-carbon sugars, ribose and deoxyribose. And then here's our disaccharides. Example of sucrose, lactose, and maltose. So all just examples of that. If we look at sucrose, again, you're going to notice what it's a combination of. It's a combination of glucose and fructose. So you'll definitely want to know that. I think I oftentimes put that on the test and on our exams. And with that, that'll bring us to our code word for this section. And that code word for the day is going to be sucrose. So again, our code word for the day is sucrose.